the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 103, where today we are going to be talking about partial differential equations.
Now, this is another opportunity for us to talk about mathematics, which is possibly one of the best things, or one of my favorite things that I would like to talk about, because a lot of people, they think of math as symbols on a piece of white paper, and I try to bring color to it because I really see it, as this scenery of mathematics. I don't know. I'm trying to paint the picture. So to anybody who likes to see beyond just math on the page, this is an amazing opportunity for me and Rayhan.
Right. Because I think a lot of partial differential equations classes in universities, or at least the one that we took, focus solely on the computational aspect of a lot of these things that we're going to talk about today.
Just the one that we took, though.
Well, yeah.
Because there is a MAT.
But is that right.
Yeah,
that might be a little more
it is.
comprehensive. I guess there are more comprehensive, but I guess the majority of people that might be, I guess the people that are really into math are already taking those.
Yeah.
But the people that are maybe just about trying to get it, they're like, oh, let me take this, and are just destroyed because you're like, what am I even really doing here? Because
Which one are you talking about?
just the one
The
that
one
we
where you
took,
took?
the one
Yeah,
that we
I guess.
took, because you're computing things that you don't really understand. So I guess we're like,
Yeah.
well,
there
we
was
try to understand.
There was a missing piece, things that they wouldn't explain that
Right.
would have made a lot of sense for them to explain, and that we thought about
Right.
while studying for the exam.
Because a big part of a lot of what you were just saying, like a way to I don't think you used the word visualize, but I think you were trying to say like the way you think about it is super important, especially in PDEs, because I think in like a good chunk of the semester, I was unable to really visualize what was going on in a lot of the things.
Yeah.
And that was really hindering my performance, more so because I think I'm a kind of person that studies to more so understand like what's really happening. So when it's just like, oh, learn that this is how you compute this, I'm like, but why? Without really understanding it. So I think it took a lot of us working together towards the end of the semester and just kind of like culminating everything towards the exam to be like, oh, wait, I think this is how that worked. And I think a lot of it came together. So I think like the thinking about it, the way you think about it, I would also say visualization, but it does become very hard when you go to higher dimensions, of course. But just like the way you think about these kind of problems, what it's actually representing, what the solution represents, like that's really important.
It is pretty funny also, because taking a PDE course or even an ODE course, I think you realize at some point that what you're doing is kind of useless, because there is no solution to a general differential equation. You can't just take any differential equation and say, this is how you find the solution. What people have done over the past, and this is why when you take one of these courses, it's like, this is the Bernoulli equation. This is the whatever equation. Like every equation has a name, because at some point in history, some guy was like, oh, look, this equation has a way to be solved. And those specific equations are the ones that we study in our courses now. So it's not just like we're going to study like partial differential equations in general. It's like, no, these are the ones that we know and that can be done like relatively by hand. And I guess like a kind of a brief sliver of intuition about how they work. And then they're like, now compute them.
No, but I should also say that they do happen to be, or not happen to be, but I guess like we also, like that's how they were thought of, like very relevant. So it's not like it's not like the ones that we learn are a very small subset of the general PDEs, even though
they are. Yeah.
I mean, of course, 100% agree. But would you say that all the other subset actually describes real world problems as well as these already do?
I think, a very big chunk of the ones that we know are directly related to like physics or
Right,
like or like
exactly
real
what I'm
world
saying.
issues
Exactly
like
what I'm saying.
finance or
Yeah.
problems that
Right,
we
right.
have to deal with in real life, and then we have like we write down the equation for the behavior and then we try to solve it.
Yeah, and most of them we've solved. Like most of the ones that are relevant to us.
I mean,
Okay,
we
like
don't really
Navier
know
Stokes
that.
and whatnot.
We
Like,
don't
of
really
course, there
know
are unsolved equations, but like we have like most of the relevant or at least right now. I guess we never know what's in the future. But I'm saying right now with what we know, at least most of the partial differential equations, I think, have solutions. And if they don't, well, there are other ways to solve it, but there are also like, I wouldn't say supercomputers, but there are softwares dedicated to solving differential equations.
Yeah.
Which is why I think majority of people kind of get derailed from, oh, why am I even studying this? But I think that's like besides the point, because I think the point of studying it is more so to like understand why, like how the software is working in the first place.
Which is like a whole field on its own,
It's
right?
just a whole
like
field
if
on its own.
if you do computer science or like I guess physical computers, I don't know if that's a thing, but like you do computational physics, that's the thing.
Computational physics, right.
And you deal with like NumPy or whatever,
Right.
or SciPy rather. They have like a numerical integrator, but there's so many different techniques to integrating systems, and it's kind of like it's a huge body of knowledge, and it's kind of your job to go in there and be like, this is the method that I should use to integrate my system, and now I will use it.
That's a good reference because there are like so many
There are a lot.
ways to integrate things in SciPy. So like
an example of
same
that is
thing.
just doing like you can do when you do rectangles, what is that called?
I mean, I know there's triangular integration.
What's an integral with rectangles? Riemann, yeah.
Riemann,
So you
Riemann.
can do like Riemann integration, which
Right,
is
right.
like it's kind of an analogy because like it's not really integrating
Just
when you're
taking
doing
some,
things,
discrete
but
sum.
yeah. So when you do like a discrete sum with rectangles, that's one way you can do it. You can also do like a trapeze way where it like connects the
It basically creates
endpoints
like a
and
histogram of your data and
makes
is
it-
doing a bunch of these things.
yeah, there are tons of different ways
Right,
using
right.
cubics, quadratics. Sometimes you want to get it's a
Yeah.
weird system, so you need to use like something that's more accurate, or else it'll blow up in some way. But yeah,
All this to say, like, there's no like one way to do it. It's just like the ones relevant to us. We found like multiple ways to kind of hack through it. And
no,
we're like,
numerical
oh,
integration is for like you can do
well,
it for
no,
the ones you
numerical
can
will
solve.
work for anything.
It's
but
for the ones that you don't
approximate,
know,
but
right?
it's always approximate, right? It's
Yeah.
not always exact, but
But
it's
good enough,
good
right?
enough. I mean, like for what?
for
For most,
for
right,
real world
right.
applications,
Right.
you can literally set your parameters in Python to be like allowed error,
Right.
and then be like
and then just
10 or 10 to the minus 10. You know, it's good enough.
I mean, I don't know if that'll run, but like I know what you mean.
Yeah.
I know what you mean though.
Yeah.
Yeah.
So partial differential equations. I guess the first thing
Oh.
that I want to talk about.
We didn't get into the.
Oh, yeah,
We didn't
yeah.
get into the.
Oh, yeah,
we forgot about
we got
the.
some.
So we got
stuff.
some news. So the first piece of news is that we hit 500,000 downloads.
Congrats to us.
That's us, I guess. We're actually at 501 right now, and kind of a surprise we didn't post it. We're a little actually busy in the summer as well, which
Yep.
which
Yes.
turned out to be very fun. But we're still going with our schedule. We have a cool interview lined up. Anyways, that's besides the point. But that was one piece of news that we hit, so that's always amazing. And just before we get into the episode, I know you're excited. Let's just finish up with the comment of the episode this time, not the comment of the week. So we have Srinath commenting, Raylev Physics with Parker and Rayhan. I think he commented Raylev Physics on another episode, which is why it's funny. He says, you two are doing a great job. Keep it up. Inviting and talking to great people of the 21st century. We people are getting international exposure. Great job for making me feel physics.
Raylev is your name and my last name.
Yeah, I think people. Oh,
Okay.
I thought that was obvious. Sorry. Yes, Raylev is my first name and his last name put together.
Yeah.
Yeah. So
That's the comment.
so that's kind of funny. So thank you, Srinath, for that wonderful comment. And yeah,
if you want to be next week's comment of the week, make sure to go on this YouTube video and leave a comment, and you might get picked.
super simple.
So yeah,
Super simple.
make sure to
Yeah.
maybe show somebody. Who knows? But anyways, let's talk about partial differential equations.
Right.
So I want to bring it back to the basics just for a little bit, just for a couple minutes. Let's talk about equations and conditions. If you have an equation, let's say it's a differential, I guess I don't think it counts as a differential equation. In some sense it would. But let's say it's just y equals some function of x. It's not really a differential equation, but it's some function of y and x and y prime, but you're not using it. Whatever. This equation, you're writing y, your solution, in terms of x, the independent variable. How many conditions do you need on this? 0. Why? Because you already have the solution. Now, if we go up to the first order, you have some equation involving y, y prime, and x. This is a first order equation. If you find the solution to this equation, it turns out there's more than one. And that's because you need an initial condition, or I guess in ordinary differential equations, it's a initial boundary value.
Oh, it is
right?
an initial condition.
Right, because there's no difference
because in this case it would be an initial condition, right?
So you need one condition. And maybe an easy example is that, let's say y prime equals 0. Your derivative equals 0. Well, I can give you a bunch of solutions to that. I can say y equals 1, y equals 3, y equals 100. So there are many different solutions, but you are required to give a condition. For example, y at 1 equals 1. Then there is only one unique solution to that problem, right? So in that case, the problem is well posed. Now, what you'll probably notice is that when you go up in order, you will need more conditions. And, I'm not going to keep pulling examples out of my head, but if you have like a second order one, you're going to have two parameters that can change. And, if you go up and up, you're going to need more conditions.
It's just like 1 minus, or I guess like the highest order minus 1 would be the number, because
technically it is n conditions, and the first condition being the solution with the parameters, and then the next conditions are the ones that are being imposed. But when we get to, I guess first I should say, when you're dealing with one independent variable, you can think of your condition as setting your solution equal to something at some point, right? Because you're on a one-dimensional line, and I say, okay, my solution is equal to this at y equals 3, or y at 3. Or you can set your derivative equal to something, or your second derivative, right? It's just a condition. When you get to higher dimensions, you have two independent variables, for example. Now your domain is two-dimensional. So your conditions now have to become broader, right? Let's say you have a function of time and space. Now, imposing a condition is like, for example, I'm setting the source of information for my solution. And when I say source of information, it's kind of like you have your general solution, which will be molded by your conditions. And then when you impose a source of information, it suddenly snaps to the unique solution to that problem. So for example, if I say that I have some function of x and t, position and time, I can say that at x equals 0, my solution equals 0. So I'm putting a source of information down at along the time axis, right? So for all points in time, my solution is going to be 0 at 0. And then, space can change as well, right? So then in the spatial side, that's when you will see like the variation and how your specific equation will be molded by that condition.
Right. Because your initial conditions are basically describing what your solution will do, right? Because we have higher level problems where you have, are we talking, I guess boundary conditions kind of flow through initial conditions. There is a difference though. Yeah. The initial condition, it's not only the time factor.
I think technically it's just like boundary and initial is the same technically.
Because I think the way that I understood it in terms of like physics, was that initial conditions were representative of time values.
No, that's what it is. But like, they're just words, you know?
Oh,
like,
so it's all just all just conditions, I guess,
like
just to solve the equation.
It's just in the language, right? If I say initial condition, I mean initially, as in like right now, my solution looks like this, but then it evolves over time.
I guess boundary.
If it's boundary, then it's spatial. I'm saying here, at all times, it is equal to something. Right. So let's talk about really quickly before we actually talk about some cool equations. Let's do partial differentiation and then like integration. I don't think it's called partial integration, but it's just with respect to
multivariable integration.
Yeah, I guess.
Yeah, right.
So now that you're going into the partial world, where actually when I was a first year, I thought partial differential equations was easier than ordinary differential equations because I like partial. It's like a part of it, you know, like it's like half.
Okay, no.
But no, that's just not right. I realized very quickly. Now you're dealing with multiple independent variables. So instead of just saying like y plus y prime plus x equals 0, which is just one independent variable, right? Where you can actually see your solution on the graph when you draw it. Now I can say things like the derivative with respect to x plus the derivative with respect to y equals 0. You're dealing with different directions. And it's cool at first because you're like, oh, like the problems that they give you are really easy. They'll say like the derivative with respect to x, y, z, like kind of like a third order, right, is equal to 0. And then it's pretty easy. All you got to do is integrate with respect to z. You just get a constant, and then integrate with respect to y. You know, a y pops out, and then integrate with respect to x, and then you get all these things, and it's going to be a third order, right? So there's going to be 3 parameters in that equation. And, you know, we get easy problems like that. But then things get a little bit more complicated when you go to like second order, or you start dealing with sums.
Well, yeah, I was just going to say, like, even if you add first order equations, it starts to get harder.
Because in one variable, you can kind of visualize it, right? If I say y prime equals a constant, then it's like, okay, right? The derivative is a constant, so therefore, whatever. But in higher dimensions, if I say derivative with respect to x plus derivative with respect to y equals 0, then you're thinking, so the derivative in one direction plus the derivative in the other direction need to cancel out at every single point, right? So it's harder to visualize. And you can't really think about what the solution will look like, right? Like if you try to think about that, like what will the actual solution be like? I don't know.
I don't think you can.
You can solve that though. I guess that is the transport equation.
Right, that is the transport equation. I mean, okay, so like down to the big meat of a lot of this stuff that I think took a little time for even me to really grasp into what we were doing in the first place is that, hey, this is like at the end of the day, or like while it does represent computations, like they actually represent things that are happening, right? So like when we're talking about things like the transport equation, so like the very example that you just gave, where you say the derivative in the x plus the derivative in the y equals 0 or equals anything really, what that's actually describing, if you take a second to think about it, is the way some kind of, well, it's technically an incompressible fluid flows. It's basically the convection equation. So that, and when you ask, well, what is it really describing in terms of this fluid flow? Is it describing where it is? No, it actually describes the density of the fluid at various points of the system. So when we're saying, for example, ux plus uy equals 0, or let's say ut, or let's say anything, I mean, it doesn't really matter. It's mainly that the spatial derivatives are added. In that situation, if you think about it, what it actually represents is a solution that states at every point an xy evolving with time, what is or how is this fluid flowing through these positions. So if, let's say, I have this gas, or technically that's not really incompressible. Let's say I have some kind of liquid that I'm not too sure on the specifics of it, but I know it's an incompressible fluid. So let's just take a liquid, for example, and let's say I'm flowing it through various pipes and something, and I make this kind of convection equation, right? So I can try to model basically how much pressure or how much density this fluid is representing at different parts of the system. So again, trying to connect the mathematical side to the real side is sometimes important, because sometimes you can lose yourself in like thinking about, well, what am I really solving for? Because the most common letter used in all of PDEs is U. So it's U sub something, and U basically represents your solution. And the problem with that is that U is like very different in everything, right? It represents something completely different in most equations. So sometimes you can tend to, again, get lost in the math and just think, okay, U is just a solution. But no, what is it really representing? Well, completely different things in completely different scenarios. So that's where the transport equation even gets its name from. And again, all these equations just get names either from people who've like invented it, like Laplace's equation, for example, or, well, examples like this, or like the convection equation, where it gets from like a process that it models.
Yeah.
Right.
So I wanted to talk a bit more about the transport equation, because
Canadian, the way you said about
Okay.
that one. Sorry.
Well,
that was just so funny.
the transport equation, because it'll lead us to understand the wave equation a lot better if we get through this. And if you're gonna take PDEs like next year or something, this is actually a really good episode to listen to about.
Or if you're taking any level of physics, you should take PDEs, is I think what you should say.
Sure. Because
Any high level of physics requires a good understanding of partial differential equations. Last year, I think like I was talking about the fact that like I did that research thing, and we were dealing like with solving all these PDEs, and like I was doing them like all on software. Didn't really understand like what is it meaning, now, like, so I would definitely recommend for anyone who is interested in going into physics, even though the math might seem daunting, it is definitely worthwhile to try to understand PDEs. Shoot, sorry, go ahead.
So I want to get this idea of information and how information travels. It's kind of I don't want to say like a different way of thinking about a solution, but it's the way that I definitely think is the best way to think about it. So the transport equation, just to be explicit, I guess it's ut, so time derivative of the solution, plus a constant times ux, spatial derivative, equals 0. That is the transport equation. And we did things called dealing with integral curves. And when you have constant coefficients like these, like here in this case we have 1 on the ut and we have c on the ux.
Wait, did you say c when you said?
Yeah.
Oh, sorry, my bad. I didn't catch that.
We have constant coefficients in front of the derivatives. Now, this technique of like integral curves is kind of a higher level concept that not even like we really understand how it totally works. But what you find out is that you can like set up these terms that have to be equal to each other, depending on the coefficients of the derivatives and if the function were to appear in the equation. There's some terms that have to equal each other. And so from there, you can basically integrate out and figure out some kind of imposed conditions on your solution. It turns out that for the transport equation, the integral curves are just like linear equations. Linear, what's the other word for linear? Affine, right? They're affine.
Isn't that to do with transformations?
Well,
but I guess
anything
affine
is a transformation at the end of the day.
Right, right.
Okay, sorry. Somebody just rang our doorbell. Anyways, so the integral curves are curves that have, or I guess, yeah, because they're general, right? They can take on any shape. They're curves that your solution will have the same value along. Right, that was not the right way to say it, but right. Yeah. So, for example, if you have lines, like let's say they're just horizontal lines, you can think of filling up your xt plane with just a stack of horizontal lines. And then along each of those lines, it will define the value of your solution, and each one of those lines will be constant.
Right.
constant
Now,
along the,
where
along
do you
those
get the
lines.
integral curves from? I think you kind of glossed over that. So it's like, I mean, quickly. So like you just, well, I guess we're not going to get into setting up
No.
the equation,
No.
but you take the equation, you set it up in a certain way. And the reason it's called the integral curve is, well, basically because you have to integrate the equation to then get the idea of the integral curve is that, let's say, easy example, just x and t, right? So in that example, if we were to solve for an integral curve, we would get t as some function of x plus a constant, right? Because we're integrating it because there's no defined bounds. So if you draw that on a tx plane, also maybe we should explain why t is on the vertical because we always.
I mean, it doesn't
I mean,
matter.
okay, well, t is on the vertical a lot in PDEs, mainly because of wave equation, I think, but we'll get into that. Wait, shoot, no, I forgot what I was saying.
Integral
Wave
curves, you're
equation.
adding a constant. To
Right.
it.
So if you think about drawing a graph where t or y equals some function of x plus a constant, and the constant can be anything, it'll just be a bunch of, well, curves or a bunch of lines. Well, they can also be approximated, or not approximated, but they can be representative curves in higher order equations. But in these situations, these lines or curves represent as well. I'm just speaking what you just. I'm just saying what you said. The solution is completely constant over. So that's kind of how you get that integral curve and where the name comes from. But it's more so, why is it drawn that way? Because, well, you're saying that this function, t is a function of this, solves this solution. That means in all of the situations where t is a function of this is satisfied, that means along those curves, the solution is valid. Or is well posed the correct term to use here?
I don't know.
The solution is correct along those, right?
I don't think correct. I think just like
Wait,
that's what it
The
is.
solution
right?
is constant along the curves, but
along
it's
the
different
curve,
along
but
the
it's
curves,
different
of course, because
between curves.
it's different between
So
curves.
I think a
right,
really
right,
good
right.
visualization to kind of understand, because as soon as you can visualize this in your head, you kind of understand the character of the solutions to these equations. So let's think about this. Let's think about just concentric circles coming out from the origin, right? So it's just like you fill up your entire plane with circles. And let's say those are your integral curves. So along each circle, your solution will be constant. But going from one circle to the next, your solution can change. And, well, how do you know what your solution is? Well, remember, this is a first order equation, which means we need a condition, right? We need one condition. And so let's say that on the positive x-axis, we set our solution to equal, let's say, x squared, right? So along the positive axis, we're forcing our solution to equal x squared. Now, what does that say about our entire solution across the entire plane, right? Well, you can just think about assembling your rings, right? Not along, but you take your rings and you raise them until they hit x, the half parabola.
Yeah.
Right? And so your solution is going to look like some type of parabolic bowl.
Yeah.
You know what I mean?
Yeah.
And there you go. There's how you visualize that. But you can put anything along the x-axis. Let's say we want a sine wave, which would have your circles kind of going like in and out, like up and down. Visually it's
a little weird to visualize, but yeah, I get what you're saying.
You can basically, and this is once again your source of information. So when you have integral curves, you have this general, I want to say, like layout of how your solution can be. And then what you're doing is you're just pulling those integral curves up and down depending on where they have to intersect your source of information, right? And remember, your integral curves can really look like anything as long as it can fill up the entire plane.
Because remember this thing, integral curves, are kind of like contours. Yeah, well, they are. They are contours, right? Exactly. And I believe we spoke about contours in some episode.
Yeah.
And literally the exact what you just said is the way to visualize contours on a graph, right? Because the issue is that contours are kind of, or like level sets, I should say, for people. Level sets are defined as where let's say, for example, we have X, Y, Z. The level set onto the XY plane are graphs, or I should say curves, are curves where Z is constant. That's just how level sets or contours are defined.
Here, Z is a function of X and Y.
Right, Z is a function of X and Y. So similarly, bringing it back to PDEs, we're thinking of integral curves as the contours, and then if we're bringing it up to now the third dimension.
Oh yeah, I guess it's kind of like reverse,
exactly,
reverse projection
we're
of
reversing it exactly. Yeah. Now we're thinking about it the other way. Instead of projecting it onto a contour map, which is what we did in multivariable, we're now thinking about it as a graph itself.
So
it's kind of interesting.
Yeah, no, that is a good way to think about it. If you were to have a graph, the way to visualize that three-dimensional graph would be to draw the lines where your function is constant and then project it down.
Right.
But here, we're telling you what the contours look like, and then your job is to bring it out into three dimensions. Right. And that will do that will define your solution.
Right.
That will be you.
That would be, yeah.
So that was pretty good. That was pretty good. Cool. Going into wave equation, because wave equation is really cool. So wave equation is UTT minus CUXX
squared. C squared UXX.
C squared?
That's just convention. C squared is just convention, and why is it convention? Wait, what? No, I know this. Why is the C squared convention?
Oh, because it has to be positive.
Right, because it has to be positive. There it is. Because the value itself has to be positive because, well, the wave equation, I guess you can kind of get from the name, represents light. Well, or at least can be used to represent light. It can be used to represent light, of course.
It's not necessarily.
I'm saying, of course. It's any wave. It's any wave.
You can think of waves on the water.
Any wave.
You can. It doesn't even have to be like real waves, right? It can be square waves or like any type of shape.
No, but I'm sure that's why they use the variable c. Because
I don't think so. No? I don't think so. No. Well, c represents the speed of the wave, but it can be anything. Right?
I guess C is also used for speed of the wave in other fields. So I guess C is a pretty general speed of propagation of something. So
it turns out that there are multiple ways to solve the wave equation. The easiest way is separation of variables, which we're not going to talk about today. The harder way, which gives you more intuition, or I guess what we just spoke about gives you more intuition onto the harder way of solving it. So you can treat your differential equation as an operator onto a function. So for example, if you have like the partial derivative with respect to x operating onto u, right? It's an operation, right?
Right.
You can write any equation as a differential operator. So for example, what I just said, UTT minus c squared UXX can be written as the differential operator of the second time derivative minus c squared times the second x derivative acting on u.
Right.
Okay. Now, for people who know about factoring and using imaginary numbers, the way you get like a squared minus another squared. Wait, actually, do we need I for this?
That's what I was thinking when you were saying before. When did we use I? That's what I'm saying. I was thinking of the exact same thing right now.
We used I at some point.
When did we use I? I don't think... Because I... Yeah, sorry. For the people listening, that's probably very confusing what you just heard. Because...
This might have been for something just different.
Because Parker and I were talking about the makeup of the wave equation. And we were talking about if it involves a plus... So basically, we're trying to make a squared minus b squared, right? Because it's uxx minus c squared. So we were thinking a plus b or a plus ib into a minus ib. But at the exact same moment, I think we both were like, wait, I don't think we need I.
Oh, it's the heat equation because it's a plus.
I is in the heat equation. Right. I is in the heat equation.
So there's no I here. I
is in the heat equation because you need the plus. Right.
So forget everything we said about I. You can break up your operator into two, right? You can have it as, think of it as like a squared minus b squared is just a plus b times a minus b. So now your differential operator is broken up into two operators. So the first one operating on u is going to be partial t plus c partial x. And your other one is going to be partial t minus c partial x. And then what you can do is you can find the solution to the first one,
Right.
and then plug in that solution to the second one, and you will find the you'll find the solution to the entire thing.
Well, the power of what you just like the ux minus c, or sorry, ut minus cux plus, and then the ut minus. Well, those are
Transport equations.
Exactly. So like that's the power of the wave equation coming from the transport equation.
Because now you can think of number one, superposition, and
Right.
number two, everything we just spoke about, all the integral curves.
Right.
So your first transport equation, we have a minus c or a plus c, right? You change the sign between the two. But those are just constants, right? We didn't have any condition on the constant being positive or negative when we were speaking about the transport equation.
No, but I mean, no. That won't affect. No. That'll affect the sign on the.
No,
on the
it will.
Yeah.
But I'm saying the general transport equation, it doesn't matter what your coefficient is.
Oh, right.
It can be anything.
Of course. Yeah.
Right?
Yeah.
In this case,
Yeah.
right, one of them is going to be positive, the other is going to be negative, but you solve it the same way.
Right.
I guess something we didn't mention is that the integral curves of the transport equation, we did say they were straight lines, but more specifically, they're straight lines with slope c. So
Right.
whatever your ut plus cux,
Right.
c is going to be the slope, or it might be 1 over c. So
No, see, here's
it's
where
related to
c squared comes from. Yeah, see, now this makes more sense to me. Yeah, so here's why it's c squared, because you need the c, because c is the speed. No, c is the speed. I'm like almost sure.
Yeah.
It's not 1 over c. And so c represents the speed of the wave. So the slope, again, when you say...
right, because the reason I was thinking of 1 over c is because we draw it. Yeah, because we draw it the other way.
Exactly. When you draw it, it's drawn 1 over c because you're doing time axis.
Yeah.
Exactly.
So here, you're in the transport equation, c is the slope. So you can just think of x as a function of time. Your thing would be like x plus ct and then plus b, some constant. We think of c as the speed of the wave. I want you to think about it as the speed at which information travels. Here's why. I'm not going to go through the math, obviously, but the solution to the wave equation, because you can kind of, I guess, draw the connection between splitting it up into two transport equations, the solution is a superposition of two transport equation solutions. And because one of them was positive, one of them was negative, that means that the first solution, or I guess the first component to your solution, is going to be right traveling. So the integral curves are going to be going right, like inclined towards the right. And the second one with the negative sign, your integral curves are going to be inclined towards the left. I don't think it's super important to note that the slopes will just be negatives of each other. It's going to be symmetric in that way. You're not going to have like one integral curve being super up and the other one is super
also,
low.
I think it's the other way around. I think minus is right.
Yeah.
Right, because minus goes the other way.
Sure.
It's equal to, because it's t's here. But yeah.
One of them is going to be right traveling. One of them is going to be left traveling.
Again, right traveling, left traveling. It's super important to also remember t is vertical. Because again, if it's not, then everything will be confusing.
Well, no, it'll be the same, but just
Nothing's
different
right and
speed.
left.
Different speed, right? Like, because you just do the
No,
inverse.
because the right traveling on a t being vertical graph is equal to
down traveling or up traveling.
Like, I don't know. I guess
whatever.
something different. So yeah. So remember, t is on the vertical, which is where we think about this, and yeah. So that's actually where you can also think about like what the solutions of these transport equation and therefore wave equation mean, coming from this one point, right? Which is like these two. Okay, well, I guess how do we define it nicely? From anywhere along the graph or along your system, the purpose of saying that your solution is defined as a superposition of two transport waves, one going right and one going left. Basically, what you're saying is these two lines with slope c and minus c are intersecting at this one point. So that means they have to have been originating from, well, somewhere, and that somewhere is usually the boundary.
Right. So we spoke about your source of information. So
And that exactly.
So think about this line of logic. If your solution is constant along an integral curve, then if I tell you that at this point, your integral curve has to be equal to 3, then at any other point along that integral curve, it is also equal to 3. So that's how you build your solution. If you figure out all of your integral curves and you match it to the boundary condition, and I ask you, what is the value of your solution at the point x, y? Well, the first thing you do is you figure out which curve is x, y on that point, and then you just trace it back to where that curve intersects your condition. And that will tell you exactly, your condition will say, well, right here, it has to equal this. And so therefore you just say, well, if we say at t equals 0, initial time, your curve equals this. This is where we use right traveling and left traveling. So if your curve is a straight line, like a slope, right? It has a slope. You say at 0, it equals this. But then that piece of information that starts at time equals 0, but then goes off diagonally, right? That piece of information travels along the integral curve and then touches the point that you're trying to find the solution. So going back to the wave equation, because this is directly related, now you have like a grid of integral curves. Some of them are going left, some of them are going right. Your solution is just the sum of the two. So let's say you have an initial condition, right? At t equals 0, you're saying your function is a sine wave, sine x, let's say. Now I say, at this point, x1, y1. What is the value of your solution? Well, what you would do is you would say, okay, well, first of all, this point is on the right traveling integral curve A. This integral curve goes back at t equals 0 and hits the sine wave at whatever point. And then you're going to say this point is also on another integral curve that's going left. But that point at t equals 0 comes from another position, right? It kind of forms like a triangle leading up to your point. It hits another point on the sine wave. And that piece of information has traveled leftwards towards my point.
Right.
Now I'm just adding those two values, and that is my solution.
And remember, because it's just a constant, these solutions are always defined like in these regions. Like no matter where you are, like you will find a left traveling and a right traveling, even if it's like, usually it's not drawn, right? Because if you would draw all of the curves, it's basically just like a continuous spectrum of curves. Yeah. But like it's you know, you can think of them because it's a constant, you can just shift it just a little bit and then you're on it, right? And this is actually where like the whole left traveling, right traveling, this is kind of powerful or it kind of defines your light cone actually, like from from Brief History of Time, I think, right? Where light cone was, So your light cone, or I mean, I don't know if it's called anything else, but I maybe I would like to think about it like as you were saying, the information cone is basically all of the information that you have ever received in your past. So if you take your position in space-time right now, wherever you are, and you draw these integral curves from where you are, basically, towards the start of time equals 0, which is from, let's say, when you were born, again, with slope c, which is being the speed of light, everything within that, spatially speaking, is things that you or your light or your eyes could have received in terms of light.
There's actually words for this. So the cone going from the past to now is called the domain of dependence.
Oh,
so
that's cool.
It is like
sense.
It's everything that can make it, like you must depend on everything that, or not everything, but everything that you depend on has to come from inside that cone.
And then you can flip it.
On the other side, it's called the domain of influence.
Right.
It's everything that you can influence. Because if you think about it, let's say right now, there is something that is 1 light year away from me. That point will only come into my domain of influence a year from now. Right?
Right.
Right now, I can't influence it. In 6 months, I can't influence it in any way.
Right.
The only way I can influence it, I guess the shortest way, is if I send a beam of light directly at it And then a year from now, boom, it will be influenced. I will have sent information
Right.
to it. And the same, if we go back to the domain of dependence, same thing. If I'm trying to depend on something, it has to be within that cone, or else it will never reach me.
And that's your light cone, and it's a pretty cool thing to think about because it all originates from PDEs and like the like how your wave equation.
Actually,
is
well,
defined.
that's just with the speed of light. Like,
Well, no, I'm saying
you know.
yes, but it's also kind of how PDEs because
Well, it's
I guess
related
PDEs
to-
depends on it's kind of
like speed of-
describing light. So yeah,
I guess, yeah.
it's kind of
no,
describing
that
light.
is
So
right.
yeah,
That's right.
you know,
But it's a cool kind of way to think about the wave equation because
Right.
your domain of dependence is going to be, if you draw back your integral curves down to the t equals 0 line, only those points between your right traveling wave root and the left traveling wave root can influence the value of your solution. Now,
Right.
we didn't talk about like time derivatives, initial derivatives. That's a little bit more complicated. I don't think we'll talk about that. But all the points in between basically influence your solution. And then
I mean, time derivatives are like more physical, I feel. Because like when you say spatial derivatives, I guess you can think about it.
No, but I mean,
But
you
when
know how
say
this.
time derivatives, you're basically saying, hey, the velocity has to equal this at this spot.
But I'm talking about like D'Alembert's formula, how you have to integrate the initial
Okay,
condition.
we don't have to talk about
Yeah,
that.
no,
of
that's
course,
what I
but
was
I'm just saying in the presence
saying.
of like higher order, like time derivatives are only given in higher order, right? So I guess
Oh,
it
they
doesn't
don't
really
have
apply to
to.
this.
They don't have to.
No, of course you need time derivatives for a wave equation. You need one time derivative for a wave equation.
Yeah, but like it doesn't necessarily have to be a time derivative.
No, but what you're trying to say is, why do you need a time derivative for a wave equation? Let's think about this. What does a time derivative mean? Does it not mean velocity? So is it not?
Like, no, here's what I was thinking. Okay, time derivative. I was saying like
No way.
initial derivative, like
Also,
condition on the derivative.
Also, wait, this is a big misunderstanding right here. U does not represent speed of the wave or
No.
position of the wave.
No.
U represents the amplitude
The
of the
amplitude
wave,
of
right?
the wave,
Exactly.
right.
That's also important. Again, difference between like transport equation, even though like it's kind of the same thing, but again, U, not the same U, means something else. And over here, it means, well, the amplitude of the wave. So yeah, what I just said was completely wrong because it does not represent the position. So UT or UTT does not represent the velocity, but I guess it does, but it represents the acceleration of the wave.
How the amplitude
How
is
the
changing.
amplitude, exactly. How the amplitude of the wave is changing.
Which
is
is
what?
not the same.
Not the
No,
same.
it's not the same. It can't be. I don't
But
think.
what even
No,
is
no,
that?
because what do you mean? Like
What
if
do
you,
you
if you have water waves, like
No, I'm
how
just thinking about
fast is
light.
it
I'm thinking about
rising?
light.
And
I'm thinking about light here. Like, what
that's
does UTT
different.
mean?
I think that's different.
I don't know.
That's different.
I don't know actually.
Also, yeah, no.
Yeah, maybe a little bit above where we're at, but yeah, maybe. Yeah, not totally certain, but again, U just meaning different things in different contexts.
Mhm. So some things to look forward to, or maybe not look forward to, is the heat equation. The heat equation is a little bit different. There's only one time derivative, right? It's uxx plus ut.
Right, UT plus KUXX. Yes,
Yeah, that's right.
Yes,
That's
yes.
right. That's
Wait, then where does the I come from even over here?
No
Don't
idea.
You? Okay,
I have no idea.
We don't know where the I comes from.
There was an I somewhere.
There's
though.
an I somewhere. We're not sure. But the heat equation, on the other hand, represents diffusion of heat.
minus k.
Oh, it's minus K? Oh, so wait. So there's definitely no I.
There is something.
So there's
there's
an
something
I somewhere
somewhere.
else. So yeah, so the heat equation is another partial differential equation that again we happen to stumble upon and say, hey, we have a really cool way of solving this. And well, it simply represents, I think the best way to say it is, well, the diffusion of heat. So for example, I think a common example I think we were given is like, for example, I keep saying that, but let's say we take a metal rod, right?
Yeah.
And did we not like
You
subject
heat
it
it
to
up.
yeah, we like
Right,
subject it to some conditions.
You heat up the center of it,
Right.
and then you see what happens.
Right, and then you see how it diffuses through the rod.
So the initial condition is basically the temperature
Right.
of your rod when you heat it up in the center. You have a distribution of temperatures. And then your solution will tell you how that heat, or I guess how the temperature changes in the
Right.
rod as time evolves.
There are actually simulations online where you can simulate the heat equation, or maybe I'm talking about, I think I'm talking about another equation, but there are like where you can basically simulate solutions to partial differential equations.
You can do it on Desmos if you just do the.
Oh well, yeah.
just
No,
write
I'm
it down,
talking
or-
about like. I guess yeah. I know. I guess yeah. You know. Yeah. Totally right. No, I guess you totally can.
Yeah.
But I'm saying where simulation, as in like you give it a rod and you give it a temperature kind of thing. Or in this case, it's a heat equation. But I remember I was looking at what was it? I think it was how the electric field propagates throughout space, and the electric field is also given by a partial differential equation. It's what it was Laplace's equation, right? So the electric
I mean,
field
it
is also
depends.
given by a partial differential equation, the way it propagates through space, and
I mean,
given some conditions of the system, like the simulation that basically set apart or what it set up was how the electric field propagates through the system. So I guess it would be similar in terms of heat equation when you're just thinking about, okay, in this case, how is the temperature propagating through the system? So again, different use, same meaning, but
I think something cool that, like, if I would have taken this course before taking second year quantum, it would have been a lot better. Right?
partial differential, where did this
Yeah.
come up in second year
Well,
quantum?
solving the Schrödinger equation.
We never solved.
Yeah, we
oh,
did.
Right.
Yeah, we
were
did. Particle in
continuously
a
solving
it was the whole
the Schrödinger
course.
equation. Right. Right. Yeah. No. Yeah, I
So
remember.
particle in a box, Schrödinger equation. Don't quote me on this. Second time derivative minus I times second position.
There's definitely an H bar somewhere.
Well, that constants. you
Sure.
know.
So IH
whatever.
bar or something.
Anyways,
Something like that.
the point of what I'm
How
trying
is
to
there not
say
a C
here.
squared? Is there not a C squared? I don't know. Some
no.
constants. Anyways, so continue. Sorry.
The point of what I'm trying to say is that we were told, okay, here's the Schrödinger equation. Along the boundary of your infinite well, your probability density has to be 0, right? Because it's infinite potential. You cannot, under any circumstance, get across that. So you're confined to a box. Little did we know, they were just imposing a boundary condition. They were saying that your solution along the boundary equals 0, and also 0 outside of that domain.
Right.
And then they essentially just said, well, okay, now solve the Schrödinger equation. At the time, we were pretty much just guessing, right? Just guessing what it would look like.
I mean, we guessed. Well, was it 0 or were we also doing like the exponential decays, or was that was not infinite?
No, we were
potential
doing that.
well?
Yeah, that was
We were also doing
the
exponential.
decays was finite potential
Right,
well,
finite
where
potential
it would
wells.
decay
Right,
into
right.
the wall.
I mean, I guess we were understanding it more actually over there, but we didn't really.
I don't know.
No?
I didn't understand like what I was going like, okay, boundary condition, set it equals to 0, and then you deal with the constants.
No,
But-
because the way that I thought about it was like, okay, if it has to equal 0 at the boundary, that means it has to have like a node at the boundary. That means it has to be like a sine wave, like it can't be like a cosine wave at the boundary. So that's a pretty intuitive, I would assume. And then like if you, for example, have a finite potential well where you don't have a 0 boundary condition, then for example, you would have a cosine wave at the boundary where it then exponentially decays outside, right? So I think like that was a basic understanding that I understood, like that I got from that. Not much apart from that in terms of like actually solving the equations,
Okay, yeah.
but just from understanding, okay, like what is actually happening with these energy levels, right? They were representing.
Yeah. So the particle in a box is a great problem to like start off.
The
in
U
quantum.
represents what, energy levels? No, or does it
U.
represent like
What's
the
U?
like the
Phi?
like the what we're solving for in particle in a box?
Probability density.
Right. I totally forgot that. Right. I see
Yeah,
different
probability.
values of U again. Different values of
Probably.
U.
In this case, it's psi or phi.
Psi.
Yeah.
See, you said phi and I got confused. You
Well,
said psi, I would've-
we use phi. And
No, you said
other
psi and I would have been like, right. But there it is.
So this is an easy problem to get started with because it's actually a harder equation to solve. But the thing that makes this easy is that from physical intuition that the probability density has to be 0 outside of the box. So you don't really deal with anything outside. And then inside the box, your potential is 0.
In an infinite.
Yeah.
Yeah, you said that.
Yeah. So then your equation actually simplifies quite a bit. Yeah. Anything else you want to talk about?
Right. So in a particle in a box, in a particle in a box scenario where it's not a finite well anymore, where it's a finite well now, then yeah. So then you have to start thinking about, well, what happens outside the box? Because again, we're looking at probability densities now. So that has a non-zero probability density outside. So now we have to account for that, and it has to go to 0 at infinity. So why was it intuitive and exponential? Because it's a complex exponential. Was it intuitive?
Okay, the reason is actually because your solution is e to the square root of a difference in energies, and what happens is that if your energy is below, because if it's a finite well, then you have like a shelf, right? If the energy of your particle is below the energy of the shelf, then what's inside the square root is real. And so it becomes an exponential. But if you're outside of the square root, then it becomes imaginary and you have a wave.
Right, and you have a wave. That's why you get the
So inside the box, it's like a sine wave, I guess, if you're taking the real part. And then outside of the box, the exponent becomes real. And then, of course, if it was
or above, it's
a second order partial differential equation, which means that you have two conditions. And if you think about this, you have two exponentials. One of them is a positive real exponent. The other one is a negative real exponent. And it depends on which direction you're going, how you set up your coordinate system. One of them has to, one of them is unphysical, basically. Your probability density can't be infinite. It has to be bounded and integrable and element of a Hilbert space.
Yeah, because from the right, you'll get one going upwards and one going to 0, and you're like, well, it obviously can't go up to infinity, so it has to go to 0. And on the left, you'll get one going downwards and one going to 0, and the other way around. So you're just like, okay, well, that happens. So a lot of this course, I think, is and an advantage. I think a lot of it is intuition. Once you understand how to solve, okay, this solves this way, this solves this way, then a lot of it is just you just have to maybe do a lot of integration, and it's a lot of applying your knowledge on solving some equations to solve something else. Sometimes we use these crazy tricks, we haven't even spoken about different coordinate systems, we probably won't, but I'm saying where you can use, and you wouldn't really think about them, the spherical coordinate change and whatnot, but it's all application of the same stuff that we learn,
I guess,
just in different use cases.
To make it easier.
Right.
It's hard to learn, but it makes it easier.
Right. So it's all just kind of tips and tricks here that it goes with this course, just ways to solve the general ones that we know or we need. So I think hopefully we brought some people some joy in terms of partial differential equations, some interest.
A little
bit.
If you enjoyed this episode, make sure to leave a like, make sure to subscribe,
comment, leave
make
us
sure
an
to
email.
Follow us and rate the podcast 5 stars on Spotify.
Also go on Instagram, check us out. We're not unfortunately
where we don't
very
post
active.
anything.
We're not active right now, unfortunately, but we're trying to be. So follow our Instagram, just math.physics.podcast. So is all of our other handles. So
thank you so much, everybody, for tuning in. We'll be here next time, which, we love to keep you on your toes.
Yep.
So this has been episode number 103 of the Math and Physics podcast. And I'm your host, Parker.
And I'm Ray. And we'll see you soon.
Bye, guys.
See ya.